Deep learning is actively emerging in the robotics field, particularly in autonomous control. Today we are going to talk about one specific application of neural networks, graph neural networks, path planning. I'm Ekaterina Mozhko. Welcome to the flipped classes about state-of-the-art topics in the field of practical machine learning and deep learning. This explanation is based on the study graph neural network-based method for path planning problems. So let's start. Historically, there are different approaches to path planning. The most distinctive directions are optimization-based methods like Dijkstra or A-star. They focus on finding the mathematically optimal path based on a cost function. Also, we are familiar with sampling-based methods like RRT or PRM. They explore the environment randomly and build paths incrementally. However, both approaches can be computationally expensive, especially in cases when dealing with obstacle avoidance. But what if we use deep learning for this task, specifically graph neural networks? Studies have proved that graph neural networks, GNNs, can significantly reduce the number of collision checks required during the path planning process, so it makes path planning process faster. The proposed method operates on graph structure data where nodes represent possible positions in the environment and edges represent potential paths between those positions. The GNN predicts edge weights, which represent the traversal cost of those edges, to determine the optimal collision-free path. But an important question might arise. How do we represent the environment? We use graphs, random geometric graphs. We generate them in each training phase. But it is worth mentioning that this graph is not related to any specific real-world environment. That is why it is called random. Instead, it connects randomly generated nodes with edges based on a fixed radius, mimicking physical proximity. We use them to expose the model to diverse scenarios, such as different obstacle layouts, different node distributions, and different path complexities. But how do we define these nodes and edges mathematically? We use feature vectors. They are the raw input vectors that encapsulate essential information like position, coordinates of the nodes in space, information about whether the node is an obstacle or not, distance from the node to the goal, and maybe some additional features. Also, we use edge feature vectors. They might include the length of the edge, orientation of the edge, whether the edge intersects or is near an obstacle. However, we do not use these pure feature vectors. We use embeddings instead. Why so? Embeddings provide a transformed representation that is more compact and useful for learning. That is to say, we focus on things that are really important to us, while preventing sparsity in the data. To compute embeddings, we use multi-layer perceptrons, just like encoders. But what do they do, actually? Firstly, they multiply feature vectors by learned weights. Next, they apply an activation function, like ReLU, to introduce complexity, so that our network can capture more complex nonlinear relationships. After this, we stack layers, and we do this process for both node embeddings and edge embeddings. Also, we get obstacle embeddings generated from a CNN. Graph embeddings are combinations of node embeddings and edge embeddings. So when we combine obstacle embeddings and graph embeddings, we get the environment embeddings. And this is exactly the format that is suitable for passing further to GNN. After retrieving embeddings, the GNN processes this information and propagates across the graph structure. It does so with a two-step process, which involves two main components of GNNs. Graph Attention Network, GAT, which determines edge priority based on distances, and GCN, Graph Convolutional Network, which collects second-order neighbor connections. Firstly, let's talk about Graph Attention Network. The Graph Attention Network incorporates an attention mechanism to assign different importance weights to node neighbors so that the model focuses on the most relevant ones. The key idea is to compute attention coefficients that represent the influence of neighbor G on node I. Attention coefficients are calculated using the embeddings of the central node Hi and its neighbors Hj via this formula. So we can concatenate weight of the current node I and the neighbor nodes. We multiply them by attention vector and apply the ReLU on this whole term. The new embedding for node I is computed as a weighted sum of its neighbors' embeddings. So we process the graph further, aggregating second-order neighbor information. We do this with the use of graph convolutional network, which aggregates information from a node's neighbors to compute an updated embedding for the node. We do so by using this formula, GCN update rule. We apply this activation function, the activation function like ReLU, on the term in brackets. For each node I, we compute the sum of information from the neighboring nodes. They are denoted by Ni. Ni is the set of them. We multiply weight matrix by embedding of each node from the set of neighbors, and add a bias term. This way we get a new updated value of embedding of the model. Okay, once the embeddings are computed using GCN and GAT layers, the model predicts the next node in the path. For a given node I, the GNN predicts the next node by evaluating the embeddings of its neighbors. A softmax function is applied to compute a probability distribution over the neighbors. And we select the neighbor with the highest computed probability. This step is repeated with iterations until the goal is reached. But why do we know that the predicted path is optimal? The key idea of this algorithm is that the GNN is trained using reference path generated by classical algorithms like Dijkstra or A-star. During training, we minimize the difference between the predicted by GNN path and the reference path. We typically do this with the use of loss function. We can use cross-entropy loss, for example. We can calculate it with this formula and get the optimal path. So let's quickly recall what we learned today. The training process of this algorithm to compute the optimal path consists of the following steps. We have an initial state and a goal state, a set of obstacles. We generate a graph. We use GNN with GAT, graph attention network, and GCN, graph convolutional network. After this, we apply attention mechanism, which combines information from the environment embeddings, obstacle features, and graph structure. And we produce unified node embeddings that encode both the graph and environment information. And then we use, for example, Dijkstra algorithm to compute a reference path. And after this, we calculate loss between the Dijkstra algorithm and the algorithm computed by our method. So today we observed an interesting topic which integrates ideas from robotic fields and deep learning. Thank you for attention.